Welcome and thank you for joining. Let's take a look at some practice questions with inverse relations. Our first example will be that of a quadratic relation. To find the inverse of a function, we start off by replacing f of x with y. That is because it makes it easier for us to simplify the equation. So y equals x squared minus 9 instead of f of x equals x squared minus 9. Now remember, f of x and y mean the same thing. So next we will invert the function, which means that wherever you see y, now we're going to write x. And wherever you see x, we're going to write y. So the equation will turn into x equals y squared minus 9. Now we need to solve for y because this is our inverted relation, and we need to solve for y in order to write the equation in the form y equals whatever it does in terms of x. So we'll have to take negative 9 to the other side, since y is already positive. And if it makes you feel any better, so rewrite it as y squared equals x plus 9, same thing. Now it's time to isolate y completely, so we'll say this is y equals plus or minus the square root of x plus 9. So we're going to give it a name, and remember that for inverse relations we use the name of the function, which in our case is function f, and then we'll write the negative 1 on top of it in the place of an exponent. Remember, this is not a power, not an exponent. And then it's just a symbol that we use to indicate that it's the function f inverted, and then plus minus the square root of x plus 9. So once we find the equation of the inverse function, we're going to graph both of them, so the inverse and the function itself on the same grid. So I'm going to make the given function green and the inverted function blue. So as you can see in here, we have x squared minus 9, which is basically the basic parabola or the parent parabola, shifted 9 units down. So that means the vertex has come all the way down here. And there is no stretch, so therefore you go over 1, up 1, over 1, up 3, over 1, up 5. Now, another way or quick way of drawing the graph of this is by knowing the roots of this equation. So x squared minus 9 would be equal to 0 at x equals plus or minus 3. So x squared equals 9, or x plus minus 3. So you would know that the roots will fall right here. So I'm just going to follow the regular parabola step 1, 3, 5. So over 1, up 1, over 1, up 3. So this would be my next point, and then up 5. And same thing in here on the other side as well. And we're going to try to extend the arms as much as we can to make this parabola look like a parabola. So precise enough. Make it better. And then extend the arms. Now, one of the things that I notice very often when I mark your work is sometimes, and I understand sometimes when we are working under pressure on a test, and the parabola will go this way and the arms will stretch out, okay? So sometimes people just do this. And please don't try to avoid drawing the parabola with the inverted arms, so it has to open up. Now, this would be the graph of the given function. Now, we have to draw the graph of square root x plus 9, and we have plus or minus in here. So to draw the graph of a square root function, when we get both the positive and the negative root, that what we have to do is draw both arms of them separately. So in other words, we're going to draw the graph square root of x plus 9, and then the graph of negative square root of x plus 9. So these would be the two parts of the inverse function, so the plus and the minus of it. Now this would be the parent function, square root of x. Remember, this is the parent square root of x, but you see that there is a horizontal translation of 9 units to the left. So horizontal translation of 9 to the left, which means that the square root function will start right here. And the square root function will operate up 1 over 1, up 1 over 3. So it operates in like parabola, but instead of going over 1, up 1, now we go up 1 over 1. Instead of going over 1, up 3, now we go up 1 over 3. because the horizontal and the vertical coordinates have swapped places. So similar to this, then, we can also think this way. So the x-intercepts of the parabola now should become y-intercepts of the square root. So that can help us draw the graph of the square root function a little bit faster. So I'm going to do it both ways. So I'm going to go here up 1 over 1, plot the point. And then up 1 over 3, plot the point again. And then up 1 again over 5, plot the point again. And then for the rest of it, just continue drawing the first arm of the square root function. Now we're going to do the other side of it. So what you see on the other side of it is a reflection about the x-axis. How do I know this? Well, remember that these are the two graphs that we created with the inverse, right? So the plus and the minus. So the minus in here is before the function, right? So before the function means it's before the y value. Before the square root is before the y values, which means that the y values have been negatived in a way. So we're going to take the y values wherever they are to the other side, in other words. So we're going to have, again, the same translation of 9 units to the left. It operates in the same way. And we're going to go over 1. Down 1 this time, over 1, down 1 over 3, down 1 over 5, and we'll see that the y-intercept will be at -3. So that will be this x-intercept of -3 now translates to a y-intercept for the inverted graph. So here we go. We'll connect the points to make this nice and pretty. And voila, this would be the graph of the inverse function. So let me just give it sort of a same tone in here. So the one highlighted in purple would be f -1 of x. And this would be f of x. So once you find the equation of the inverse function, you draw the graph of the inverse function. And another thing that we need to take care of is the reflection line. Now the reflection line is the line that starts at the origin of the Cartesian plane and has a slope of 1. So the line y equals x. Now why is it y equals x line? Remember what the inverse relations are about. Inverse relations are about switching x with y, which makes x and y equal to each other in the inverted function. So the x of the function is the y of the inverted function. The y of the function, given function, is the x of the inverted. So that's why we say that they are reflections about the line y equals x. Now, next we need to find the invariant points. So as you can see, here we see the invariant points. Remember, invariant points are always points that don't move due to reflection. And the points that cannot move or don't move due to reflection are the ones that are already on the reflection line. And the points that are on the reflection line for both graphs are these two. So obviously you see that these are also common points of the graph and the inverted and function or relation, we should say. So these are common points of the parabola and the inverted parabola, so these two, but they're not invariant because what has happened in this case is that this point on the green graph has gone right here on the purple graph, and this point in here on the green has gone to the other side. So, sorry, this one here has gone right here, okay? So the only invariant points are the ones that are on the y equals x line. Now, as you can see here, it is kind of hard to estimate the coordinates of the invariant points. So what we're going to do is find them algebraically and write them also in exact form. So how do we determine invariant points algebraically? Recall that invariant points are on the reflection line. They belong to the graph of the green function here. So the green graph, or the function with the green graph, the function that is highlighted in purple, and the reflection line, so these two. So if you want to look at or find the invariant points, it means that these are points that belong to both graphs. So we can use either the given function or the inverted function to find the coordinates of the invariant points. So it is best to use the given function just to avoid any mistakes that you can get as a consequence of getting something wrong, like hypothetically, right? So it is best to use the equation of the given function to find the invariant points. So since the invariant points are on the y equals x9, then we can also say that the invariant points are on the graph of the given function and on the reflection line, which is y equals x. So we can look at invariant points as points of intersection between the given function and y equals x, which is a reflection line. So one way of looking at invariant points is as if we are trying to solve the system of equations y equals x and y equals x squared minus 9, which is the given function. And from here on, we can find the point of intersection. And as you can see, since we have just y on the left side, we can make the right sides equal to solve or to determine the coordinates of the invariant points, so the x values at the invariant point. So here we have x equals x squared minus 9. And continue solving this quadratic equation. So bring x to the other side, so that will become negative x, and then minus 9. And that would be equal to 0. So next we have to solve this equation. Obviously it's not factorable. Can't find two numbers that multiply to negative 9 and add to negative 1. So we're going to ask for help, quadratic formula. So for using quadratic formula, then we have minus negative 1. And then we have plus or minus square root of negative 1 squared minus 4 times 1 times negative 9 over 2 times 1. So x equals 1 plus or minus. So see here you have a 36 positive and a 1, 37. So root of 37 divided by 2. So as you can see here, we obtain two x values. The reason why is because we have two invariant points. So the coordinates, well, the x coordinates at the invariant points are 1 plus root 37 over 2, and x equals 1 minus root of 37 divided by 2. So with two invariant points, we found the x values at the invariant points already, then we are ready to state the coordinates now. So we're going to have the first and the second down here. Now, I want us to think again. Invariant points are on the line where y and x are equal. What we just found were the coordinates of x. So 1 plus root 37 over 2, that's the x coordinate of the first invariant point, which I'm thinking should be this one here, and 1 minus root 37 over 2. So if you were to determine the y coordinate, considering that invariant points are on the line when y and x have the exact same value, then we're going to say that the y value is also 1 plus root 37 over 2, and for the other point, 1 minus root of 37 over 2. So you can either find the invariant points by using reasoning and understanding that invariant points are the intersection of the reflection line with the given graph, or a reflection line with an inverted graph, right? Or we can follow the 4 little steps that we have mentioned in class, which I am going to add in here. So remember that if you want to find the invariant points, so this is just another way of finding the invariant points. It's not really very different from what we just did, but it's sort of a shortcut. It doesn't really explain why we do it the way we do it. So another way of finding invariant points. But it can be very practical and easy to remember. So if we want to find invariant points, we set f of x equal to x, because f of x means y and y would be equal to each other at the invariant point. So if we have the equation of the function in the form y equals x squared minus 9, then we make y equal to x. And then x squared minus x minus 9 equals 0, and then you solve the equation from there. It's exactly the same thing. So it's sort of a shortcut of what we just did in here. Now, it is a practical way, as I mentioned, to find the invariant points, because it doesn't really explain all the details of how and why we find the invariant points the way we do. But it can also be confusing, and this can be one of the drawbacks to it, because it can be confusing because it's kind of similar to how we find the inverse of a function. So what I would do to find the inverse of a function, follow the 4 little steps that we mentioned in class, and to find the invariant points, take the graph of the given function and the graph of the reflection line, put them together in a system, and solve for x. Once you have the values of x, then you can state the coordinates of invariant points, which will be exact same value. I hope this made sense, and thank you for learning with me. Bye for now.